Alright, the next thing I would like to talk about is logarithmic decrement. Let me write it down. Alright, the logarithmic decrement is a quantity that is very useful when we look at pretty much experiments about vibrations. So what we discussed so far is looking at the properties of the structure, and from the properties of the structure we can determine how the structure is supposed to behave. Because we started from, for example, the value of the stiffness, the value of the mass, the value of the damping coefficient, and then by looking at these three quantities we can determine the equation of motion, and then from the equation of motion we can determine the solution of the equation of motion, which is x as a function of t. So which means that from the properties we determine how the system behaves, how the displacement occurs. Now in this field, when we talk about vibrations, very often we actually need to do the opposite. We need to look at a certain structure, see how the structure behaves, and then from the behavior of the structure we should be able to obtain the properties of the structure itself. So doing experiments means that, for example, we can use shakers, we can use shaker tables actually, and then we use typically we use accelerometers to determine how a certain structure behaves, how a certain structure vibrates when it is subjected to an external input. Now, of course, in order to do this, we need to go through a certain modeling of the behavior of the system in order to obtain the properties of the system itself. And one way that we can, one quantity that we can use is exactly the logarithmic decrement. Now we can start by defining, by looking at the formal definition of the logarithmic decrement. So if we look at the formal definition, it is given by the natural logarithm of the ratio between the amplitude at the generic time t and the amplitude at the time t plus period. So how can we write this mathematically? So the logarithmic decrement typically is indicated with the letter delta, so with the Greek letter delta, and then from the definition that I just gave we can write as the natural logarithm of x at a certain time t divided by x at t plus uppercase t, where uppercase t is the period of oscillation of the system. So I'm going to give the definition again. So now that we have the equation, so the logarithmic decrement is given by the natural logarithm of the ratio between the amplitude at a generic time and the amplitude at the generic time plus period t. Now if we consider the underdamped response that we found previously, we have that our solution would be, the generic solution will be x of t a times e to the power of negative zeta omega n t multiplied by sine of omega dt plus phi. This is, remember, this is valid when zeta is between 0 and 1. Remember this function here? So now that we have the function of the displacement with time, we can simply use this function here and we can plug in our definition of the logarithmic decrement. So on the numerator we will plug this exact expression. In the denominator we will plug the expression of the x as a function of t plus the period t. So let's see how it looks like. So we will have that delta is going to be equal to the logarithm, the natural logarithm of a e. So e to the power negative zeta omega n t times sine of omega dt plus phi. We said that at the denominator we have to plug the value of the function after a certain period t, uppercase t. So which means that instead of using lowercase t, we will use lowercase plus uppercase t. So it becomes a times e to the power of negative zeta omega n. So here see I put lowercase t plus uppercase t multiplied by the sine of omega t. Same thing here, instead of putting only lowercase t I'm going to put lowercase plus uppercase t plus phi. We know the relation between the period and the damped frequency for a underdamped system, and we know the relation is t equal to 2 pi over omega d, which means that we can obtain that omega dt is equal to 2 pi. Now the goal would be to simplify a little bit this expression here. So we can look at this quantity here, sine of omega d t plus phi, and let's see how this expression becomes. So if we start from sine of omega d t plus phi, we can simply multiply omega d by lowercase t and uppercase t, so this becomes omega dt plus, excuse me, this is the lowercase, plus omega d uppercase t plus phi. From here we know that omega d uppercase t is equal to 2 pi, so we can simply plug this 2 pi here we know that the sinusoidal function is repeated every 2 pi, because you know it's a periodic function, so it means that sine of omega dt plus 2 pi plus phi will be equal to sine of omega dt plus phi. Now if we plug this quantity here, this will be very helpful to actually simplify this expression, because what we obtain is delta equal to the natural logarithm So the numerator, of course, stays the same. For the denominator, I replaced this expression here with this expression here because we found that they are equivalent. Okay? Of course, this expression here is the same of what we have at the numerator, so we can actually further simplify this one. So we can get rid of this sine function because they are the same on the top and the bottom. We can also get rid of this amplitude here because it's the same amplitude. So basically what we obtain is the following. So it will be e to the power of natural logarithm of e to the power of negative zeta omega n t. Also, this expression here is an exponential where we have a summation here, lowercase t and uppercase t. So we can split this as a product between two functions, one that is e to the power of negative zeta omega n lowercase t, and the other one is e to the power of negative zeta omega n uppercase t. Yes. To the 2 pi here? Yes. So here we are looking at a function, a sine function of a certain quantity plus a phase plus 2 pi. We know that sine, yes. So you can get rid of this 2 pi and the function will be the exact same. So at this point, so after we plug this here, we do the first simplification, we can split this exponential function in two terms, one that has the lowercase t, the other one has the uppercase t. We can further simplify because this is the exact same of this one. So we do this other simplification. What we obtain is natural logarithm of 1 over e to the power of negative zeta omega n t uppercase t. So here we have a logarithmic function, here we have an exponential function with a negative exponent, so it means we can bring this at the numerator, so this becomes natural logarithm of e to the power of positive, in this case, zeta omega n uppercase t, logarithm of an exponent. We know that they are one the inverse of the other one, so we can basically get rid of these two, and then what we obtain is finally that delta, remember we started from delta, is simply equal to zeta omega n t. So I want to give you 1 minute to go again through these steps. So now, of course, in order to make it useful for us from a typical experimental point of view, we can actually take the expression of t and write t as a function of zeta, because basically zeta is the parameter that we are going to we are searching for. Remember, in this case we are starting from the behavior of the system, which is the x of t, and from the behavior of the system we are trying to find the properties. The property that we are looking at right now is the damping ratio. So in this case now we have the relation between delta, zeta and t, so we can express t as a function of zeta, so we'll have a direct relation between delta and zeta. So the period t, we know that is equal to 2 pi divided by omega d, which means is equal to 2 pi divided by omega n square root of 1 minus zeta squared. So when we plug this expression here, we have that delta will be equal to zeta omega n multiplied by what we just found for the period, so 2 pi omega n square root of 1 minus zeta squared. Of course, we can get rid of this omega n and this omega n, and we finally find the expression of the logarithmic decrement as a function of the damping ratio. Makes sense? We said that what we want is to find the damping ratio as a function of the logarithmic decrement, which means that we simply need to take this expression here and rework it in order to have our zeta as a unknown. So basically what we have is that zeta is going to be equal to delta divided by square root of 4 pi squared plus delta squared. So this is the expression of the damping ratio as a function of the logarithmic decrement. So how do we practically use this expression here? What do we do with this expression here? Yes, both of them, the logarithmic decrement, which is, as we can see from here, related to the damping ratio, they tell us how quickly, as you just said, the vibration will dissipate. Right? So, as we said before, in order to use this equation, we need to start from an experiment, basically. So we start from taking an accelerometer, we attach the accelerometer to our structure. The structure is vibrating. When we see the signal from the accelerometer, would look like I'm doing qualitatively something like this, for example. Remember, it's a damped free system, which means that in order to use this equation here, what we need to do, we need to go through actually two steps. The first step will be to find delta from the curve that we see, from the x of time. For example, if this is t1 and let's say this is t2, we can simply find delta as the natural logarithm of x of t1 divided by x of t2. Once we have this value here, we can actually plug in this expression here into so that we can find zeta. So basically we start from the actual behavior of the system. Again, we see how the displacement changes with time. From this measurement, we can actually determine the amplitude at two consecutive peaks, for example, and then by using these two numbers we can calculate delta, and then from delta we can calculate this expression here, or we can simply plug this here and then we have the expression of the damping ratio as a function of two consecutive amplitudes. Make sense? Any question? Yes. Yes. So how we came up with the period? So this is something that we obtained from the expression of the relation between the frequency and the period. So frequency and period are related to each other through this quantity here, through the 2 pi. And we know that the period is basically how long it takes to complete one cycle for our system, and then omega d in this case is the damped natural frequency, so is the number of peaks that we have in one unit of time. So these two quantities are related to each other through the 2 pi, so we can write this expression here, and we also know that the damped natural frequency and the natural frequency are related to each other through these two expressions here. So this is how we found our period t, and then we plugged here, and then once we plug here, this is what we obtain. Since we have natural frequency here, undamped natural frequency, undamped natural frequency here, we can simplify, we can get rid of these two, so we have the final expression of the logarithmic decrement. We can rearrange so that we obtain the damping ratio as a function of the logarithmic decrement, and then here are the two steps that we use to actually determine the damping ratio. Make sense? Sure. Other questions about this? Alright, if there are no other questions, we can actually look at an application problem, which is this one. So I'm going to read the problem. So we have the free response of a 1000 kilogram car with a stiffness of 400,000 Newton per meter is observed to be of a form given in the figure, which is pretty much the same that we saw before. Modeling the car as a single degree of freedom oscillator in the vertical direction determine the damping coefficient if the displacement at T1 is measured to be 2 centimeters and 0.22 centimeters at T2. So please spend 1 or 2 minutes to think about this problem. Alright, we are back. So again, here we have so this is the response that we have for the system. We know that the mass is 1000 kilograms, the stiffness is 400,000 Newton per meter, and then we know that the amplitude at T1 is 2 centimeters and the amplitude at T2 is 0.22 centimeters. So how do we proceed in this case? How do we find the damping coefficient? No, they are asking for C, because C is the damping coefficient, Z is the damping ratio. So let me put here damping coefficient. And of course the two quantities are related to each other. So I would say we can start by looking at the relation between damping ratio and damping coefficient. This is one of the equations that we wrote maybe last week. So in this case we have the relation between the two quantities. If you recall, the damping ratio is the ratio between C and C critical, where C critical is simply 2 times square root of km, or we can also write as C divided by 2 m omega n. So from this relation between damping ratio and damping coefficient we can write C, remember this is what we have to find, damping coefficient, is equal to zeta 2 square root of k times m. Now k is given, m is also given. What we have to find is zeta, the damping ratio. How do we find the damping ratio? We can find the damping ratio by using the expression of the logarithmic decrement that we just found. So we have the damping ratio zeta is equal to delta divided by square root of 4 pi square plus delta square. And we also know by the definition, from the definition of the logarithmic decrement, that delta is equal to natural logarithm of x of T1 divided by x of T2. Now, from the information that we have from the statement, we can actually determine this quantity here, because we have x of T1, we have x of T2, so we can calculate the natural logarithm of the ratio between these two quantities, or we can simply take this and then we can plug here, and then we can take this one and we plug here. So if we do all the steps in order to obtain the damping coefficient, what we see is the following. We have C is equal to the natural logarithm of x of t1 divided by x of t2, and then at the denominator we can put 4 pi square plus, again here we have delta square, so we have to use again this expression here, the natural logarithm of x of t1 divided by x of t2, and this is squared, multiplied by 2 square root of kn. Makes sense? So this quantity here, the logarithm of xt1 over xt2, is the same that we have here. This will be our delta. This whole expression here is the expression of zeta. Since we have to find C, we can plug zeta here, so it will be zeta times 2 square root of km. So this is zeta times 2 square root of km. When we plug all the numbers, because now we have all the numbers, we obtain that C is equal to 13256 kilograms over seconds. Make sense? Any question about this problem or this concept in general? Alright, if there are no questions about this, we can close for today and for this week, and by the end of the day tomorrow you will find an homework on Canvas, and that will be due Friday next week by the end of the day. Sounds good? Alright, I'm going to stop the recording now.